Hi, I'm Seth Chandler from the University of Houston Law Center, and today for the Analytic Methods for Lawyers course, we're going to be talking about roughly 100 Wolfram Language vocabulary words. And the motivation here is we've got a course that's going to be covering substance, but it's also going to be taught using Wolfram Language, and a number of words you need to know in order to be able to have any comprehension. So the idea is to stick them together in this one video. I don't expect you to understand everything after this talk, but at least you'll have been exposed to the words. And without further ado, let's get going. All right, so I want to divide this up into a few sections. We've got general purpose words, we've got pattern language words, we've got statistics functionality, which I'll just speak on very briefly, and we've got some keywords that might help you at the end. All right, let's start with the general purpose words. We have the most common thing I use is list, and list is just a container for data. Um, it can hold basically anything, and here's how you write it, or one way to write it. You write the head list followed by comma separated arguments for the things that you want to include in the list. So here I've included a number, another integer, a string, and a plot. And as you can see, the elements of the list don't have to be of the same type. They can really be of any type that you want. Any Wolfram language expression can go cheerfully in there. So if I evaluate this, what you're going to see is that we get back what I put in, except that it does evaluate the plot. But you'll see that instead of having list as a head, instead it has these curly braces. And this is actually the more common way of representing lists. It's what Wolfram language is going to output by default in the front end. And usually when I write list, I don't write out the word list, nor does anybody else. They put it in these curly braces. Your friend. Rule. Okay, the rule has many purposes in the Wolfram language. Usually it's to help transform one expression into another, but there are other purposes for it. And again, we're going to write it this way to begin with. We're going to write it with the head rule, followed by what we want to plug in for, and then the second argument is going to be what value to give when we plug it in. And so you can see when I evaluate this that it doesn't write back rule. It write backs the common short form, which is an arrow. You might want to know, well, how do I make that arrow? And if you just go with a hyphen and a greater than sign, that's an arrow. Okay, so that's the simplest way to make an arrow. All right, so how do you actually use it? Well, here's a list. This slash dot means plug in or replace all. And by the way, you can see when I hover over the operator, it very thoughtfully tells you what it is. And then here's our rule that we're going to replace it with. And so when I run this, what you see is that the A has been replaced by a 6, and so the output is 6, 7. Here I'm using the short form instead of the more full form that I'm showing here. Okay, so that's rule. We'll see it a lot. Let's go to times. Um, times I use a lot, I guess. I guess we do a lot of multiplying in this class. And so if you want to multiply two together, you just put times and then the numbers that you want to multiply together. By the way, it doesn't have to be just one number. It can be as many numbers as you want. Okay. Um, Here's the more common way of doing it. If I simply write, let's actually write this out. If I write 4 space 3, it understands that that's multiplication, and it puts in a little gray 3. And if I now execute that, it will give me 12. By the way, here is how not to do it. 4x3. It doesn't, it thinks, okay, you want me to multiply 4 by the x by the 3, and that's 12x. So don't use x as a multiplication operator. If you really want to write it out, you can do this. You can do 4, and I'm going to do backslash square bracket times close square bracket 3. And that's good if you really want to be, elaborate about it, but really just putting a space works fine. All right. So 4 times 3 is 12. You can multiply a number by a symbol, and if I do so, I get 3b. Okay, there are lots of cousins of other arithmetic operations that work in exactly the same manner. If I want to add two numbers together, the head is plus, or I don't have to do it that formally. I can make it look more like real mathematical notation, and it'll be 2 plus 3. Okay, so if I want to divide two numbers, the formal head is divide, but I can use the short form slash. Also, I can write this as, watch this. I can take 11, I hit control slash, that creates a little fraction bar and a placeholder, and there we go. Now we have a nice little fraction. I can take numbers to powers. So I'm taking 2 to the 5th power, which is 32. 2 times 2 times 2 times 2 times 2. Instead of writing out the word power, I can use the short form of a caret or a capital 6 in some sense on QWERTY keyboards. Or if I want to get snazzy about it, I can make it look two-dimensional and have a more conventional form. And so I can write it this way. Let's see how I do that. I write 2 control 6 5. Okay, so that's how you make the pretty little um, superscripts there. Okay, set. Set is used all the time. It's how you assign a value to a symbol. So supposing basically I have a symbol C, I evaluate it. I've never assigned anything to C before, so when Mathematica doesn't know what to do something, it just spits it right back at you. But now from now on, I want C to be 11, or at least until I countermand that order. And the way we do that is we write the head C, and we then follow it with what symbol we want to use to store the minor, store the expression, and then what the expression is that we want to store. Okay, so that could be set C11. You'll notice, by the way, that it doesn't have to be something that is already evaluated. I could say set C12 divided by 4. Okay, and now it returns 3 because it's actually done the computation. But let's go back just so everything stays synced and make C 11. And so now when I ask it, hey, what's C? It tells me 11. Now, you're very seldom going to see it written out this way. Everybody uses the short form of the little equal sign. Equal is what we use for assignment. We don't use left arrows as in R. We use equal, which is what most computer languages do. So there we go. All right, next let's talk about function, an extremely important concept in Wolfram language. Functions are sometimes known in other languages as lambda expressions, but in Wolfram language they're just called functions, which is what they are after all. So here's how you define a function. You specify what the argument to the function is, and you specify what the function does. So this says take any x and square it. So if I apply that function to the number 3, I get 9. There are other ways of writing functions, and let me show you. Here's one which it's more of a mathematical notation, and it has the little function arrow. You might ask, how do I make the function arrow? And the answer is, watch me right now. X, vertical bracket, vertical bar, hyphen, greater than, space, x squared. Okay, so that's how you make it. And you can assign a function a name. You can say, from now on, square me is the function x goes to x squared. And so if I now say, what is square me of 7, you can use it like any other Wolfram language function. So that's function. Function has a cousin, which is slot. And so instead of writing the function as a function of some symbol x, you can simply write it as, look, saying, take the first argument and square it, and take the second argument and add the two together. So slot is basically what slot in the argument list is being referred to. So let's see if we can understand how this works. If I take this same function that I just defined and I apply it to the first argument being 3, the second argument being 1, it's going to say, well, 3 squared is 9 plus the second argument, which is 1, so that's 10. Let's just make sure that works. It does. And just as you could assign a value to the function I showed you before, you can assign a value, a symbol to a function defined using slots. Okay, so here we go. And in fact, we can do something even simpler. And this is how you'll often see it done. Um, Instead of writing the word function around it, you use the little hash sign here. This is for a one argument function, whatever you want it to do, and you finish it with an ampersand. So an ampersand following an expression means that's a function, and so we're going to apply that to 3. So if you see, and let's just do one more here. Let's do hashtag 1 plus hashtag 2. And now we'll apply that to the function 2, 3. And if I've done this right, I hope you realize I'm about to get 5. All right. So again, this is just using the slots without having to write out the word function. Okay. So uh, part. I showed you list before. Let's now take a look at part. And part is basically a dereferencing operator. It's how you get information out of a list. So suppose I want the second item in a list. It's just part, whatever I'm trying to get information out of, and then whatever position it is that I want. Okay. What if I want multiple positions? Well, you just wrap up the parts in a list. So here I'm getting the first element and the fourth element. Now, what if we have a list of lists, which we certainly can have in Wolfram language? Here's a list of lists. Supposing I want to take the second list and then I want the first part of it. Instead of wrapping the part specifications in a list, we're just going to put them in sequence. And by the way, we're going to see something very much like this in query up ahead. So this says take the second part of the first level and the first part of the second level, and we get our 7 out. There's another notation for part, which you'll frequently see, which is the double square brackets. You'll see that here. So this is simply saying, get me the second part of this expression. Here I'm saying, get me the first and the fourth parts. And here I'm saying, get me the second part, and then of that sub-expression, get me the first part. Okay, so that is part. It's now time to take a look at the other major data container in Wolfram language, and that's association. So instead of having numbered parts in which you access the pieces with a numerical index, as we just did, instead you can use whatever you want, basically, to this is sometimes called a hash in other languages, or a key hash, or I don't know what else it's called, but those are some of the most common names. Um, and so here we're saying, look, if you want to dereference it, call 5 by Texas, Arizona goes to 3, and Florida goes to a plot. So again, you can have very heterogeneous elements inside your association. And you can assign an association like virtually anything else to a symbol. So here we'll call ASOC the association of these key value pairs that I've set forth here. These are called key value pairs because they are pairing a key, Texas, Arizona, Florida, with a value, 5, 3, blah, blah, blah. How do we get information out? We can use that same part operator, uh, or, and here's where it's a little tricky, because association is also a function in some sense. You can apply that function to a key and get the value out. So here, if I say, what is association of Florida, I'm going to get this plot. If I say, what's association of Texas, I'm going to get 5. Okay, let's go back to where it was, which I think was of Arizona. Yeah. All right. You'll notice that isn't true of lists. If I say, take a list and apply it to 2, It says, I don't know what you're talking about. And when Mathematica doesn't know what you're talking about, it just spits back what you had. Okay, so now let's put two things together. Let's put functions with associations. Here's a function that says, for some A, take the Texas part of A and square it. So here I've written it using function notation. This is what it looks like in a more full form. And now if I say, what is Tex squared of ASOC? Remember that ASOC had a value for Texas of 5, and so I'm really asking it to square 5. Again, there's a short form, which is instead of using a numbered slot, I can use a word slot. Here it's saying take the Texas part and square it. There's our friendly ampersand to make sure Wolfram knows it's a function, and apply it to ASOC, and I get 25. So that's functions with associations. Onwards to compound expressions. Compound expressions are simple. They're just a way of putting multiple expressions together. First, let k be 34, and then let m be whatever k is. 34 minus 5. So if I evaluate that, I get 29. Short form, so you don't have to write out compound expression. You just put things inside parentheses. And if you put multiple statements inside parentheses separated by a semicolon, you get a compound expression. You should note that Mathematica will only basically return the last thing that it evaluates. So the value of this expression is 29. It's not 34 and 29. It's just 29. Okay. So we have the official Wolfram language, which is all the stuff that's in the documentation, but they've recently permitted individuals to develop their own functions, which are peer-reviewed, and they are, although they're not part of the official language, they nonetheless are very well documented, and you can use them easily. So if you go to here, I'm going to open up a web browser, and I'm going to go to resources.wolframcloud.com/function repository, and I now need to drag this into the Camtasia window. Just give me one moment here. This is one of the early videos I've made for this course. I might not be as experienced as I will be later. And here you can see the Wolfram function repository, and it has things that you might like supposing I want to find a function. I think it has something to do with counting items, and maybe I think it's called item. And so it now will search, and it's going to find a bunch of stuff, and there's what I'm looking for, item counts. Okay, so all sorts of stuff. We'll pull that away. But basically, you now are accessing a resource function. And by the way, you can evaluate that. I'm now going to hit Apple return on Windows. I don't know what it is, but it's something like Apple. And we hit that, and you're going to see, if all goes well, that it's going out to the web. And it takes long. And Wolfram Language has lots of built-in functions, but in recent years they've permitted users to extend the language by adding functions of their own that go through a peer review process that are extensively documented and that work to all intents and purposes like built-in functions. These are kind of like packages in other languages, and so these are called resource functions. So let me show you how you use one. I'm going to push down on my keyboard Shift, Option, Command, Apple, and R all at the same time, and I get this little box. I'm now going to type the name of the resource function, which happens to be birdsay, and you'll notice it's giving me a little help and suggesting that's what I mean. All right, and so there it is. I can get more information on it if I want there. I can get help, but for the moment, let's just run this function, and you're going to see that it produces something. So um, to find out about resource functions, there is a Wolfram language site you can Google. Just do resource function Wolfram. It'll pull up the site. It's got search bars, all sorts of fun things that you can look up. There are three resource functions that I realize I use an awful lot. I don't use birdsay very much, although it is fun. And those are apply level, power total, which I'll come to later, and terse, and I need to do terse now. It's a very useful function. So what terse does is sometimes Wolfram language, although it tries to sort of iconize really big outputs, sometimes it doesn't do it the way you want. And so terse lets you have some control over the size of output. So here are 100,000 numbers, okay? Um, and instead of printing every single one of them out, which would be quite a production, terse says, oh, produce about 8 lines of the stuff. You'll notice I think it actually is producing 7. It's an approximation. But, and you'll notice, by the way, this little skeleton here, which says that there are 99,886 terms missing. So you will often see me use terse. I might use it like this, using the afterthought notation that I spoke about in a prior video, or at least I hope I did. Uh, and so you might see me do something like this, where I'm emphasizing, hey, build a table, and as an afterthought, oh, you know what? Just print 8 lines of that. Okay. Um, In fact, I think I'm going to leave that in the permanent notebook. Let's look at plot, one of the fun commands. Okay, so this plot lets you plot univariate functions, one variable function. So here's our expression to plot. Here's the domain over which we want x to go. I'm going to assign this plot a name, which means I can do things with it. Um, and there we go. It produces a plot. Like lots of Wolfram language functions, there are zillions of options you can use to decorate the plot. We've got a whole discussion later in the course on visualization. But just so you see, for example, supposing I want grid lines to appear to help orient us, I'm going to put automatic, and now it prints it with grid lines. All right, so that is plot. There are, like I say, zillions of options. We will come back and spend a lot of time on plot. Okay, what about total? Total does what you think. It totals a list of numbers. There you go, total. You can total at different levels. So supposing I want the column sums, 1 plus 7, 2 plus 8, blah, blah, blah. I'm going to use 1 to designate that as a second argument. Or supposing I want the row totals, I'm going to use 2 in a list to do that. And what if I want the total of the whole darn array? I just put 2 without a list, and we go down. All right, power total. This is a resource function. And what power total does is best seen with an example. Here I'm saying power total of 3 and apply that to ABC. Okay. And here's something you'll notice. You'll notice that A and B are blue, whereas C is black. And that is because A and B have not been defined yet. But C, remember way back in the video, I assigned it, I think, the value of 11. So let's just stick with this and see what it does. And you're going to see it cubed 11, and it added that to A cubed and B cubed. Okay, so if I clear C, which is a command that should know. Now C is no longer defined as 11, and now if I do this, it's A cubed plus B cubed plus C cubed. If I made it power total of 4, it would be A to the 4th. If I left it blank, it thinks I want the square, and so there you go. All right, map. Mathematica, or Wolfram language, is what we call a functional language, meaning that functions are first-class things. They're just like anything else, and therefore you can make a function an argument to another function. So let's watch us do that. All right, let's create a function f. What f does is it takes a number x, it subtracts 3 from that, and it cubes it. All right. And if I hadn't cleared C earlier, I would be having this problem of a lingering definition, but I did actually clear C, so C is now blue. But let's map F over A, B, and C. And what this means is first apply F to A, then apply F to B, then apply F to C. And since originally these things were wrapped up in a list, wrap up your answer in a list. So and there, this is because I have not yet told Wolfram language, I forgot to tell it, hey, here's what F is. I didn't communicate from the front end to the kernel. All right, and now when I do it, although this is actually useful because it shows you exactly what's going to happen. It's going to apply F to A, F to B, F to C. But now it does this. You'll notice that I can also apply it at different levels. Here we've got kind of an array, which is a list of lists. By putting this a little 2 there, it means burrow down, go to the second level. All right. I would say that's a fine point. If you don't grasp levels right away, don't worry too much about it. Equal. Equal does not mean assign. Equal really means equal to. It's asking a question. It's saying, are these two things equal? So does 6 equal 6? Indeed it does. Does 2 plus 2 equal 5? Not since 1984. And does 5 equal 6? No, it does not. You'll notice here what I've put is I've put equal, equal. That's how you define, that's the short form for equal. This is going to give me, it's going to be very unhappy because what it's saying is I'm trying to assign 6 to something that's not a symbol 5, and it's going to give me an error message. So what you want is equal, equal, and by the way, confusing equal, equal, equal. Equal, remember, is set. The single equal sign means that's a whole different story. Anyway, the single equal sign means set. Double equal means is it really equal? All right, right composition. Right composition, I think, is best defined as and then. It says first do one thing, then do another thing. So here I'm going to right compose 3 different functions. This says take your number and add 6 to it, then subtract 5 from it, and then multiply whatever you've got by 3. And I'm going to do that to 8. So we should get, let's see, 8 plus 6 is 14, minus 5 is 9, times 3 is 27. And lo and behold, when I do this, this is what I get. There's a short form of this slash star. Okay? You are going to see all, I'm a fan of right composition. So here's what you're going to see. What we're basically doing is creating a pipeline of functions, applying it to 8. These are the same functions I used here. I'm just using it in the language. Produces very elaborate constructions. Here's an association. And supposing I don't want it as an association, I just want it as a list. And so it's basically going to simplify it. Here's something we're not going to work a lot with, which is a sparse array, just to show you that it's some complicated thing. And if I say normal, it's put in a simple form. Okay? You see me writing normal, it's just to put things in a simpler form. Query. Basically, there's a whole book that can and is being written on query, but it's a metaprogramming function that basically creates a function, but does so by using the positions of the functions in the query. So that's very complicated sounding. Let's see if we can look at this. We've got a list of associations here, don't we? We've got one association with height and weight and another association with height and weight. And what this is going to do is it's going to say get weight at basically the second level of this expression, so that's 200 and 176, and then total it. And in fact, and so you get a 376. If I look at the normal form of the query, it's going to say, look, map weight over what you've got, so that's going to get 200 and 176, and then total your response. Query is a complicated function. We will see it a fair amount. You're not going to get it right away, but you've now been exposed to it. Table. Table is nice and easy. It's just a way of making lists. This says it's basically sort of an iterator in Wolfram language. It says let x go from 3 to 23 by 4s and return that. So we get 3, 7, 11, blah, 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 blah. We can have a different expression here. Take x as it goes from 3 to 23 by 4 and take those and square them. Or supposing we don't want regular intervals, we say, look, I want x to first be 3, then be 9, then be -2, and then be 5, and take that and square it. So you get the result. Okay. Show. Lots of graphics objects in Wolfram language, and sometimes we want to basically overlay one over the other. Command overlay, which can help you do that, but really the better way to do it for now is show. Show just says take two graphics objects that are of the same type. Here's a plot, here's another plot, and put them over each other. Okay? We can do it with 3-dimensional plots as well. Here's one plot, 3D. Here's another plot, 3D, and overlay them. You'll notice that show can itself have options. And here, for some reasons I don't want to go into, I might want to adjust the vertical plot range over which the final result is displayed. And so I can adjust that. I could do all sorts of things here. I could, I don't know, change the background color to purple, which would probably look hideous. Yeah, hideous. All right, so let's get rid of that. Back we go. Okay, replace all. We actually saw replace all a little earlier. I had to sneak it in order to show you what rule did. But replace all means take the first argument and plug in values from the second argument. Or you can take multiple plugins. Here I'm saying let x be 5 and y be 2. Start with xy, and we get 5, 2. There's a short form, which is ubiquitous, which is the slash dot. So if you see slash dot, that means plug in. And the right-hand side needs to be a rule or a list of rules for replacement. Mean does exactly what you think. Okay? Takes the average, arithmetic average, the end. List plot. List plot creates scatter plots. Here are a bunch of points in 2 dimensions. This says plot them. List plot says plot them. Tons of options, tons of other things we can do with list plot, but this lets you know what it is. Information. Information is a way of sort of getting the documentation without having to go to the help browser. Not that it's difficult, but here I'm getting information on map. Also, some Wolfram language expressions have the ability to get selected forms of information. So one of the ones we're going to see a lot is categorical distribution when we use statistics. And here I'm saying, get me the probabilities property on that categorical distribution. And it's saying the probability of heads for this very bad coin is 60% and tails is 40%. With lots of computer languages have scoping constructs. And the idea of a scoping construct is you might want to use a name, but you might not want to have it pollute the namespace of the rest of the document. Like with that C before, remember how that C kept lingering on? And what if I just wanted to use C once, just for this function? So there are lots of ways of doing that, but one of those is with. So let's show the classic experiment. Here, I'm setting a global definition. Z is 4. So the kernel now thinks, hey, when I see Z, I think 4. This now says, though, hey, for right now, Z is 5, and I want you to add that 5 plus 6. So I'm not going to get 10, I'm going to get 11. But just to show you that Z lives on, that this was only a temporary definition, if I now say, hey, what's Z plus 6? It's going to say 10, okay? With. If you use Z and define it in the with, you can't change its meaning later. You might it's inconvenient, but actually knowing that something cannot change its value is often very valuable, and so it's going to object, saying, hey, you already told me that Z was 5. Now you're telling me that I'm supposed to assign 7 to 5? Can't do that. I'm never going to let 7 be 5. Module. Module is essentially like with, but it permits exactly the sort of reassignment that with forbids. So here, this is saying, hey, before you don't plug in for 5 yet, wait. And now take 7 and reassign that to Z. That's module. N. Mathematica loves exactness. And so if you tell it what is this divided by this, it's going to tell you, oh, it's exactly that. But often that's not very useful. I really don't know what that is. And so you can ask it, hey, what's the numerical value of that? And it's going to tell you. That's all that I've done here. You'll also see me use n using afterthought notation. So here's what is n of 4/3. You'll notice it's coming up with a reasonable number of digits. If you want more digits, an argument. And here I'm having the fun of figuring out pi to 1,000 decimal places, just for the heck of it. We can do 100,000 places, but we'll stick with our 1,000. All right. So onward. ABS computes the absolute value of real numbers. It also does it for complex numbers. In this course, doesn't really matter. What's the absolute value of -2? It's 2. If it's not a number, it's just going to spit it back. Less. Less is equal, it's asking a question. It really means, is it less? Is the first number less than the second number? And 5 is less than 6, but 6 is not less than 5. You don't usually write it this way. You write it with that little symbol. Uh, and Not sure why I put this in the notebook, but 5 is not less than 5. Oh, I know why I put it in the notebook. About ties. For ties, you have less equal. Less equal asks whether it's less than or equal to. The first argument is less than or equal to the second argument. So now less equal 5, 5 is true. We would seldom write that. We'd write it this way. How do I make that symbol? Watch. 5. I'm hitting that angle bracket. I'm hitting an equal sign. And now it's smart enough, the front end is smart enough to say, oh, you just made a less than or equal to sign. And so I'll help you out and get it pretty. All right. Greater. I hope I don't have to go through this. Greater is like less, and there's another one, greater equal, like less equal. All right. Solve. Solve is the thing you wanted in your 7th grade algebra class, and it lets you solve various equations and inequalities. It does huge numbers of things. But supposing I know that a plus 6 is equal to 9, and I want to know, hey, what's a? The command that does that is solve. And by the way, I think this would be a useful time for me to show you a little shortcut. I'm going to click once, click twice. I've now grabbed that part of the expression. I'm going to hit Apple return, which is command return, I believe, on a Windows machine, and watch. See how it made it nice and pretty? It's called an in-place evaluation. And so it's going to produce a nicer form of it. All right, but let's undo that if I can. That was Control Z to undo or Command Z to undo. And so now let's solve this. And it's going to give me a list of rules. And you might ask, why is it giving a list of a list? And I'm not going to tell you that for right now. Just realize that it does. All right, we can do more complicated algebra problems. Here's 2 variables. Um, and trust me, solve can do a lot more. Dot. Maybe at some point in your life you encountered the dot product, but dot is basically a form of multiplication, or it's like multiplication in certain respects. It's going to say, let's walk through this. It says take 2, multiply it by 4. Okay, I'm holding that, that's 8. Take 3, multiply it by 5. I'm holding that, that's 15. And then add the 2 together. So it's an inner product in which the first operation is multiplication and the second operation is addition. And so at the end of the day, if you remember, 23. Again, we don't usually write dot. We put a little dot there. Okay, so that's a period, and that's how we write a dot product. Doesn't have to be just 2 numbers. Here I'm multiplying or dot producting one list by another list of symbols, and there you go. Log. You remember logarithms? Logarithm. So what's the log of 10? It's 2.3 because that means that e, that hideous number e to the 2.30259 power, is 10. What if I want to use a different logarithm base? What do I want to know? Hey, 10 to what power is 100? It's going to tell me that's 2 by using the log. Apply. Apply says, look, you've got an expression, it's got a head. Here, the head of this list is actually list. Maybe I should have written it this way. And it's going to say, plug in, instead of having list be the head, override it, make Q the head. Okay, so if I do that, it just says now says Q of 3 and 4. And the short form, which is at. So that's the short writing apply. And you might say, why is that useful? Trust me, it's incredibly useful. Here's one sort of trivial thing. Supposing I have a list and I want to add 2 elements together. Yes, I could use total, but I could also use plus at. Apply has a cousin, and it's the resource function apply level, written by yours truly, that basically says, lets you apply a function, in this case, the abstract function u, at whatever level you want. And so here we have some highly nested thingy bob. And at the end of the day, I want u of 1, 2, u of 3, 4, etc. And apply level lets you do that. You'll see me apply leveling a lot. Thread. It basically zips multiple lists together. In fact, I believe in Python it's called zip. or maybe it's Julia, one of them. Um, so it says, look, take the first one of here and combine it with the first one here and the second one here and combine it with the second one here and wrap a Q around it. Okay, so that's thread. If one of the elements is constant, it's always going to be 4. You don't need to write out 4, 4. You can simply write 4, and it will then say, I'll take A of 4 and B of 4. Okay, so a convenience. Values. You remember associations are key value pairs. What if I just want the value part? That's what values does. Here's our association. It's going to get the values out. Values has a cousin keys. Just get the keys out. Range. Range is a simple way of generating a list. I don't have to use table if it's something really simple. It just says, look, go from -3 to 4. Go from -3 to 4 by 2. If I leave out the first argument, it assumes it's 1. This says go from 1 to 6. You can use it with decimals, so that's range. First, supposing you have a list, you want the first element. Guess what command you use? First. Supposing you want the rest of it, you just type rest. Manipulate. Manipulate is a great Wolfram Language function because it lets you make things interactive within the front end. So supposing I have a plot, here's what the plot looks like, but I have this little symbol A here, which is undefined, but I'm going to say, look, let A go from 0 to 2, and you pick it with a slider. You'll notice the syntax is really similar to that of tables, so remember the table syntax. And so now I can wiggle my slider, and I have a built-in little sign plotter. Manipulate can use much more elaborate controls. Here's one that I'm just swiping from the documentation. But basically, it's letting you solve all sorts of complicated differential equations for various initial conditions. All right. Argmin. Argmin finds the minimum of expressions. Here's an expression. It's a paraboloid. And I want to say, find me the values of x and y that minimize that expression. And so it's going to say, oh, that's 3 and 4. Out. Out. Mathematica remembers. It basically remembers everything you've done in your session. And so if you want to get, hey, what was the 6th thing I evaluated? Out 6 will do that. I don't have to write the word out. I can write the word or the symbol percent. Now, supposing I don't remember what output number it is. I just want the last thing I did. That's just standing by itself. Okay? So if you see percent, that means it's a pronoun. It means that, or yeah, that. Entity. Wolfram Language has lots of information about the real world that you can just use. And so we have an object, an entity Houston, and I want to know I have a property, what's its population, and so it's going to compute that. If I want to know, hey, what do you know about Houston? I can say, hey, what properties do you know? And at least potentially it knows all these things about Houston. For some of your projects, you may want to use the Wolfram knowledge base, but there it is. Length. Length counts the numbers of top-level elements in an expression. Often we use it with lists. So it happens that there are 10 little elements here, and so the length of it is 10. Dimensions is when usually you would use it for a multi-level object. Here I've got, what is this? It's a 3 by 4 kind of matrix-like thingy. And so if I say, hey, what are the dimensions of that? It's 3 by 4. What if it's not regular? What if this one has 5 elements and this one has 2 elements? Well, all it can say is, look, you've got 2 elements here, and so the dimensions are 2. All right, let's talk about derivative. Derivative is that calculus thing that maybe you had at one point in your life. This is saying, hey, take a pure function object and calculate its first derivative. If you don't remember how to do this, don't worry. But if you ever do need it, there it is, and it creates another function object. Or I could say, hey, take the second derivative. Uh, Or I can take a partial derivative. Say I have a function of two variables, as I do here, and I want the derivative of the function with respect to its second argument, not with respect to its first argument. That means take the 0th derivative with respect to the first argument and the first derivative with respect to the second argument. All right. Won't be using that quite as much as I think I will be using D. D is like derivative, but it's when you have an expression rather than a function. And so here I'm simply saying take the derivative of x squared with respect to x. That's 2x. This is saying take the second derivative. And this is saying, hey, this is a partial derivative. You've got an expression that has multiple variables, x and y in it, but take the derivative of it with respect to y. If you don't remember your calculus, don't worry, just know that Wolfram Language supports these various calculus operators. But I don't use it that much, so here you go. All right, select filters, and in fact in other languages it's called filter, but the idea is here you've got some you've got some expression, and I want to find all the numbers that for which prime q applied to them is true. So basically, in some sense, it's saying map the second argument over the first argument and only return those values for which that test is true. So here's a list of prime numbers. You don't have to use a built-in function as your test. Here I've written a little custom function, and you can see why this little quick ampersand notation is useful. It's just a short little thing. And so this is saying find me every number in this list that's greater than 37. And Wolfram Language can do logic, and so often you might want to satisfy multiple conditions. The true, by the way, in Wolfram Language is true with a capital T, but no rest. False is with a capital F. And so if one thing is true and the other thing is true, then the expression is true. And if one thing is true and the other thing is false, then the expression is false. And if anything, you can have and applied to multiple arguments. And if any in that list are false, then it's false. There's a short form, which in Wolfram Language is the double ampersand. It's an infix notation for those of you who like that term. Like plus is an infix notation where it goes in between the arguments. And so this is basically the same as and, true, true, false. And because there's a contaminating false, it turns out false. Great. Chop. Sometimes when you're working with numeric evaluations, there are little tiny numeric errors that creep in that you know are wrong. Chop basically says take very, very small numbers and take them down to what they're supposed to be. So minimize. Minimize is like sort of argmin that we saw before, but instead of just returning the values of x and y, it also tells you what the value is at the minimum. Array reduce. Array reduce is a lovely function added in version 12.2 of Wolfram Language that says the following. Here we've got some two-dimensional thing. It's been put in matrix form. And I want to say take the mean of that, but go over the rows, okay? Whereas here with 1, it's saying go over the columns, and it's saying take the mean in each case, okay? So it's saying take an operation and apply it in a certain direction, actually here it's this way, over the object, okay? String template. String template is called string interpolation in many languages, and here's one that every phone chain uses. Dear, first insert, we see the car warranty on your second insert is about to expire, and so here's what we're going to fill that in with. The first insert is Mr. Chandler, and the second insert is Impala, and so here's what it produces. Okay? And just for fun, there is a Wolfram language called speak, and so I'm saying speak that, and I don't know if you can hear it. All right, and that's when you hang up. So, data set. Data set is a hierarchical container that holds lots of information. It presents with a nice syntax. Here's one that's built into the language. I'm going to get the data on planets using planet data. And we can then, this is why I showed you query, We can run interesting queries on this. This says get Mars, get its moons, now get the mass of those moons and compute the mean. So this is the mean mass of the moon of Mars. All right, list plot. List plot is like a scatter plot. I'm sorry, list line plot is like a scatter plot, but the points are joined together. So here's a list line plot. Map thread. I showed you map, I showed you thread. Now let's mate the two. So we're going to wrap up our sub-arguments here in a list, and we're going to say mate 3 with A, mate 4 with B, etc., and stuff a U in front of it. Map thread. Association thread, another sort of thread-like thing, but it says to make an association at the end. First argument are all the keys, second argument are all the values, and association thread stitches them together in order to form an association. Seed random. So this is a little difficult to explain, but oftentimes we want, especially in these notebooks, I want to be able to predict what the answer is because I want to have text that explains things. And so every time I run a random number generator, I don't want to write my text. But so what you do is you seed the random number generator so it's in some consistent state. And so you'll see me using seed random a lot. So if I run seed random, I just pick a number out. And now I say, get me 100 numbers from 0 to 10. Okay, it did that. Now I say, do it again. And you'll notice the numbers are different than they were here because the random number generator has changed every time it calls a random number. But what if I want to regenerate precisely these random numbers? I just seed it with the same seed. And so now, if I run my random number generator again, I get the same 9029 thing that I did before. Flatten. Remember I showed you we have nested lists. What if I want to denest them? So I just want to turn this into one big list. So that's flatten. There's more complications to flatten, but there it is. Group by. Group by says, hey, you've got some data. Here are the numbers from 1 to 100. And I want to group them into an association in which the keys are the possible values of applying a function to those values. And the values are what values within my original argument are associated with that key. So that's what group by does. And hopefully you can see here that here are all the numbers that aren't prime. And here are all the numbers that are prime. Okay. Take. Take is a little bit like part. It says here's some structure. Grab the first two of them. It's grabbing contiguous elements. Or here I'm saying go from arguments 3 to 4, grab those. Quantity. We haven't seen Wolfram Alpha integration yet, but supposing I want to ask a question. I don't know how to program this. I have no clue how to program something. So I'm going to say, the first thing I write in my front end is equal. I get an orange equal, kind of orange is the color of Wolfram Alpha. And now I ask it a question. We'll ask it maybe a different question. How far is it from Houston to Princeton, New Jersey? All right. And it's coming up with an answer. You'll notice it's brown. And by the way, you'll also notice it's going to tell me, hey, in the future, dude, this is how you could actually write it formally. Okay. And you'll notice the use of these entities here. But this is actually, it's brown, meaning it's a quantity. So supposing I just want the number, here we'll reevaluate this. And supposing I just want the number, that's quantity magnitude. So you can have units in Wolfram language, which is very useful. Okay. If is a function, and it says, hey, the first argument is the test. The second argument is what if the test is true. And the third argument is what if the test is false. There's actually a potential for a fourth argument. So this is saying, look, if psi is greater than 4, return 6, otherwise return 23. And you can assign the value of if to an answer. It returns a value. Here, it doesn't know what to do because I've never told it what psi is. So now I'll tell it, hey, psi is 9. And now, if I evaluate this function, it's going to say, ooh, I know 9 is greater than 4, therefore I will return 6. Okay, let's stop here for just a moment. Back we go. Okay, so now I want to cover graphics functionality because one of the things Wolfram Language is best at is producing pretty pictures because the human mind is fantastic at understanding things based on visualization. Thank you, lions and other things in our background. All right, so graphics is the head that will surround various graphics primitives, and here's a funky little picture you can make using graphics. You'll notice that if I make a plot and I say, hey, what's the head of that plot? The head of that plot is graphics. So there are things other than graphics that can make graphics objects, among them plot, parametric plot, list line plot, blah, 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 blah. All right, supposing I want a three-dimensional thing. The head is graphics 3D, and again, we're going to wrap enclose various graphics primitives, some of which only work in three dimensions, like you can't have, to my knowledge, a two-dimensional sphere, or it's not called a sphere. And so here's a little pretty picture in three dimensions. Again, there are functions you can call like plot 3D or parametric plot 3D and a bunch of others that will end up producing something that's a graphics 3D object. It's important to know what your head is because if you want to show two things together, they need to have the same head. So if you try to show a graphics object with a graphics 3D object and overlay one on top of the other, Wolfram is going to sensibly object. All right, what are some of the directives that you see me use? Um, if sometimes you want to combine directives, like supposing I want a dotted purple line, that directive is a little wrapper that makes the Wolfram kernel understand that, hey, this is a single directive in some sense. I use opacity a lot. So here I'm going to make my surface uh, purple, but make it somewhat opaque. Um, so there we go. And in fact, just because I never have any fun, let's do this. Let's let the opacity be defined by opac, and we'll say let opac go from 0.01 to 0 to 1. I could do 0, but then it would disappear. And then you can see it's, actually I need to move this up. You're going to see that it gradually gets thicker and thicker until it becomes so opaque that you really can't see the lines behind it. Okay, there you go. Point. Ooh, just erased too much. Um, right. What I originally had was this, yes, and I forgot what it was, 0.6 maybe? Get rid of the manipulate. Point. This one's not too hard. That's the x coordinate, that's the y coordinate. And now I have a graphics object, and I'm just adding an option to graphics to tell it, hey, put a frame around it. You can have point also works in three dimensions. You give it an x coordinate, a y coordinate, and a z coordinate. Point size. Oftentimes you want the points to be big. So point size is the graphics primitive that lets you do that. Color data. Color data is a function that creates a function that creates colors. So supposing I want rainbow colors, okay? So here's I now have a function that produces rainbow colors. And in fact, let's do something here. Let's call this rainbow. And now let's do this. Let's do manipulate rainbow of x as x goes from 0 to 1. And let's watch as my color changes right through the rainbow, right through, well, I guess it's this way. It's Roy G. Biv. Okay, wasn't that fun? Come on, dude. Let's get this working. All right. Also, instead of using names, there are certain numbers. This is an indexed color, so this creates a palette having 13 colors. So there's color 3, there's color 7. And you can also say, hey, I like crayons. And so here's burnt orange for the UT fans. And that's what I'm going to talk about with graphics. We'll see a lot more graphics in the weeks to come. All right, pattern language works. This might be when you want to go get a cup of coffee or stretch because this might be the most complicated thing that we do, and unfortunately, it's probably one of the most important, and I've just put it together in its own little sector here. All right, we're going to cover basically 4 words: blank, pattern, set delayed, and optional. There are many other words, and as I mentioned in the text here, I didn't understand how Wolfram Language worked when I first got it in either late 1992 or early 1993. I can't remember. Um, and after about 2 weeks of playing around with it, the light bulb went off or on. And really, it's the key to understanding an awful lot of what goes on in Wolfram Language. So let's make sure you get this. All right. One other uh, Wolfram Language vocabulary word here, which I don't actually use that often, but in order to understand what the other things do, you need this vocabulary word, which is match Q. So match Q says whether the this argument here matches this pattern here. And in fact, let's just double check that I've got my argument sequence right. Yes, it's saying, does this expression match this pattern here? Okay, so does 37 match 37? You bet. Does 37 match 38? Nope. Does A match A? Yes. Does A match B? Nope. All right, so that's fine, but that's not going to get you very far. We need a more expressive language. So the simplest pattern matching thing is the blank, which you can write as blank with nothing in it, just like this, blank. Okay. Um, and this is saying blank means it basically matches any single Wolfram language expression. So is 37 a single Wolfram language expression? Yes. So it says true. Is A single Wolfram language expression? Yes. So it says true. Is a plot a single Wolfram language expression? Actually, it is. Um, and so, as I've mentioned before, there is a short form, which is the underscore for blank. But the problem with blank is it's like the person who says yes to everything. It's the ultimate yes person. So we want to be more choosy. And so here we're going to say, hey, I only want you to match if the head of the expression I've given you is whatever this thing is, this argument here. So if I say match Q of this list, it's saying, is this a list? And it's going to say yes. If, for example, I were to say, is this a graphics? It's going to say, nope, that's not a graphics. All right. Um, so you could use it this way. You could write blank list, but nobody does that. You don't see the full form here. You see it in this more convenient form, the underscore followed by the desired head. Okay. And as you can see here, this is saying, wait a second, the head of this expression isn't list, it's you, therefore it doesn't match. Okay. Blank has some cousins, blank sequence, which is this, and blank null sequence, which has a short form of this, but this is enough for a day. All right, so we're making progress. We've gotten to blank, but now let's have a problem. Supposing I want to write a function, and it says anytime you see something, add 62 to this. So I write, hey, anytime you see something, add 62 to that something. Okay, so let's see if this works. I'll say, what's P of 3? And I'm hoping I'm going to get 65, but no, I'm not. Um, and so that's not good because the problem is here. See, this is blue. It doesn't know what X is. So what I need to do is to tell it, hey, when you see an X on the right-hand side here, that's not just any X, that's the thing that you've stuck in after P. And the thing we want for that is pattern. Pattern says, when you see something on the right-hand side, that is X, use it. So let's define this. Okay, and now if I write P of 3, it's saying, oh, wait, 3 is X, and therefore 62 plus X is 65. And what's P of 5? It's 67, okay? Again, you almost never write it this way. You write it this way, X underscore. And this is saying from now on the right-hand side of this expression of the set delayed thing here, which I'm going to come to in one moment, um, this x is the same thing as that x, okay? This whole pattern matching thing is what Stephen Wolfram basically worked out when he was 27 and younger, which was 7 years after he'd gotten his PhD and he'd gotten his MacArthur Genius Grant and all the other things that make him extraterrestrial in levels of intelligence. Okay, so what this means is you can have what are called polymorphic functions. The same head, but different argument patterns. This says, hey, what if I see a p followed by two values? Now I want you to take the second value and subtract it from the first value. Or what if the first value is an integer, has a head of integer, and the second value is y? I want you to multiply it. So now let's see if you can understand what's going on here. If I say, what is p of 3.2 and 2.2, you're going to see it does produce 1. Why is that? Well, it doesn't match this because the first argument isn't an integer, but it does match this. So I'll use this definition, and so it's going to give me a 1. What about this? It's going to say, well, this matches the integer. I'll use this pattern. Okay, and 3 times 2.2 is 6.6. You might be wondering, well, why didn't it look at this first? And that's because it's smart enough to know, let me look at the more specific things first. It's like in law, if you have this is the general rule, and this is kind of a special rule. Okay, you use the special rule first. So we've seen blank pattern. This means set delayed. This means even if y was defined, don't use that y. Don't use the global y. Wait. Don't say this means x minus 58. Wait to evaluate this until you're asked to. Okay. One more thing which is optional. Sometimes you want a function that takes one argument but has the potential of taking more. And you want to give a default value. Usually y is going to be 3, and so you don't want to make the user write it out all the time. So what you do is you just wrap it up in optional. And you say, here's the pattern that I want you to match on, and here's the default value if you don't see it. So this is saying q of x is x plus y, and in general, y is 3. So if I now write q of 5, I get 8. I don't have to write out the 3. I could do this, but supposing I don't want y to be 3. Yeah, I know usually it's 3, but today it's not. I just put in a second argument and I override the default. So that is pattern matching in a little nutshell. Let me just collapse that down, double click on that. And you'll be very happy to know that all I'm going to do with statistics functionality is just sort of expose you to, there are a bunch of things we're going to see, and you can look forward to it. So that is the end of the very long discussion on roughly 100 Wolfram Language vocabulary words. It's here as a reference for you. As I said, I don't expect you to absorb this. This is like, seeing your 100 first Mandarin words and thinking that you're going to immediately remember that Mao is cat, which is the only Mandarin word I remember. Um, and so it's like any other language. You learn it by hearing it, and you do even better if you try to speak it and flounder around. So thanks for your attention, and that concludes this discussion of Wolfram Language and 100 Wolfram Language vocabulary words.